Hello, so I'm Laura Lewis. I was muted in the first bit. So welcome to the class. We're going through exam paper on the volume and pressure and particle theory. So we're going to start with this. It's a mock exam that we're going to go through today. So it says number 1, explain in terms of the motion of particles how a gas exerts a pressure. Okay, so in terms of motion of its particles, have a look at that. So the question is asking us in terms of particles, how a gas exerts pressure. So we obviously don't have to write about particles. So if we think about, I'm going to get a whiteboard up. So if we get a plain whiteboard, if you think about a balloon, let's draw a balloon. Just before we answer that question, let's think about it. So we had a balloon and we had particles inside it. So gas particles inside a balloon. Okay, so it's sort of blown up a little bit. There's gas particles inside it. So what these particles are doing, they're moving. So they're moving in random directions. Okay, so because anything that has a temperature above absolute 0 is moving. Okay, so the gas particles are moving around and they collide with the walls of the balloon. Okay, so they collide with the walls of the balloon. So let's go back to that slide. Okay, so how a gas exerts a pressure. So gas particles, there's 3 marks this one. So gas particles collide with the walls of the container. They collide with the walls of their container, because it's not necessarily a balloon, it could be inside an aerosol can or something. Of their container. Okay. So when they actually do, they exert. Okay, so they sort of push, so they exert. So exerting a force on the container. Okay, T container. This is a pressure. Okay, so if you remember the equation, that pressure, it helps know the equation to answer this question. So pressure equals force over area. Okay. Okay, so it's force exerted over an area. Okay. Let's go down the page a bit. Oh, it's made it smaller. Let's go down the page. Oh, okay. Down the page. Press the other button. Okay, so explain in terms of the motion of the particles, the change in pressure caused by lowering the temperature of a gas. So if you think about that, gas particles are always moving as long as the temperature is above absolute 0. Okay, then so in terms of caused by lowering temperature of the gas. So the change in pressure is caused by lowering. So the hotter the gas, the obviously the more energetic the particles would be. Okay, so in terms of motion, it's particles, the change in pressure caused by lowering the temperature of the gas. So conversely to that, if you think about, so let's do it one bit by one bit. Let's change the colour. So the hotter a gas is, the greater the amount of energy the particles have. So if a gas is hotter, the particles have more energy. Okay, so this is said about lowering temperature. So conversely, the lower the temperature, the less energy they have. Less energy. Zoom out again. Just going to go for more. Go back. Yeah, okay. Less energy, yeah, figured it out now. So less energy the particles have. Get my pen back. Oh, less energy the particles have. Okay. So if the particles have less energy, they will collide with less force. Have less energy, or lower energy that we'll go for. Lower energy, they will collide with less force, lowering the pressure. Oh, force. Lowering the pressure. So you can think of a summary for that. Okay, you can think of a summary that the higher the temperature, the higher the pressure. So this is a bit of extra, okay, for notes. So higher the pressure, oops, I should say so the temperature. You could do it that way around, but just be consistent. The higher the temperature, the higher the pressure. Obviously, the lower the temperature, the lower the pressure. Lower the pressure. Okay. Move on. Oh, it's kind of moving out of that. Let's move that down. Okay. 2A, so it's a bit of a practical one. So your practicals in class, they can ask, this is how they ask it in an exam. They ask about a practical, okay? To be honest, you wouldn't have needed to do it in real life, but obviously that you would do it at school because you probably could figure it out, but and say that you tells you enough in the question if you're able to figure it out. Okay, so let's have a look. So it says a student investigates the specific heat capacity of cooking oil. Okay, so cooking oil, not water. The student, you might have water at school, turns into a different liquid. The student uses the apparatus shown in figure 1. So to have a look at a thermometer, obviously to measure the temperature, an immersion heater. There's a heater that goes into a liquid to heat it up. So making sure that I'm still volume still on. You've got a joule meter, so that measures the energy going into the immersion heater in joules, and a power supply. Okay, that just supplies the joule meter and the immersion heater. So explain one way. So you've got one way. It's going to be quite easy because it's only one thing. Giving a reason for your answer. The student can reduce unwanted energy transfers from the apparatus. Okay, so there's two main ways, and you only have to mention one of them, but I'll mention both. Okay. Way number 1, you could just put a lid on it. Yeah, it's that easy, but with a little bit of explanation. So you can either have put a lid on the beaker to prevent heat being lost to surroundings. Okay, prevent heat being lost to surroundings. Okay, another one would be to insulate it. So you could put the whole beaker into a styrofoam cup, for example. So, or I did that in my experiment, I did in the class. Or place beaker into an insulating sort of surround, or you could obviously tape it to the outside, such as a styrofoam cup. That's what you drink out of. Yeah, you might go to like a festival or something, or like an event, and it'd be a styrofoam cup you drink some tea out of or something. A styrofoam. Oh, styrofoam. Styrofoam. Cup to prevent heat loss again. So to prevent thermal energy loss, we'll say. So thermal. Move down a bit. That's fine. So thermal energy loss. Okay, definitely got 2 marks there. There's 2 things you can't do, they're both correct. Okay, oh, where's my balloon? Get to the next slide. B, let's zoom in. Okay, so a student heats 0.2 kilograms of cooking oil until the temperature increases by 20 Celsius. A joule meter shows that 6,680 joules of thermal energy is transferred. Calculate the specific heat capacity of the cooking oil using this equation. Okay, so it looks much worse than this, doesn't it? All it is putting numbers in. Okay, so don't even need to rearrange. Let's get my pen. Okay, yeah, fine. Okay, so specific heat capacity. Okay. We're just copying out the equation and putting numbers in. Okay. So there's change in thermal energy. Okay, so it says 66880 of thermal energy, so that's that. 6680 joules over or divided by mass 0.2 kilograms and kilograms already, so I don't have to convert anything. Okay, times change in temperature. Okay, so they've already told us a change 20. Okay, so we're going to get a calculator up to show you what's going on here. Calculator. Okay, you actually don't need a scientific. So 6680. Make sure you type it in right. That's the main thing. What I'm going to do is draw some brackets around that, because when we do it on our calculator, we're going to have to put brackets around it. Bracket. It's good to do it on a scientific calculator by hand, obviously, but I'm just showing you what's on the screen. It's best to do it and to learn how to use a scientific calculator. Okay. So let's just type that. So let's just make sure we've got that correct. So double check something. Yeah, this is why it's better to use one by hand, because these are not overly that clear. Okay, so see, when you saw that 4 come up, that's when we wanted to sort of point out to you, that's just working out the bottom. So always careful to use these sort of calculators. Okay, so it's 6680 divided by 4, 1670. Always be careful of that, but yeah, it's best to use sort of a hand calculator, much better for working out them on your phone or computer. Because be a bit careful with the phone and computer. If you know how to use it properly, that's okay. But I would prefer using the sort of a hand, one of those sort of Casio ones. 1670. Okay, 1670, and the units are already there for us. We could have worked out those units because that's 20 degrees and that's kilograms, that's joules per kilogram per Celsius. Okay, but they've already got them in for us, that's fine. Okay, what's the only question on that page? Okay, next question then. Okay, so there's a few things for this one as well, a few answers that you could give. So it says explain why the temperature of a gas cannot be decreased indefinitely. See, this is a thing to underline, isn't it? Because you could easily misread that, because I actually misread that. Okay, it's a good thing to underline. People highlight, some people underline things. So why it cannot be decreased indefinitely. That definitely means forever. So why you can't decrease it forever. So it's a bit of a hint here, because I mentioned something earlier, absolute zero. So let's just start writing that. So the colder a gas becomes, okay, the slower the particles move. Okay. So at a certain point, they would stop. They can't slow down forever because so it slows down up, it just stops, isn't it? At a certain point, the particles stop. And this is called absolute zero. Okay, this is known as absolute zero. Absolute zero. Also known as 0 Kelvin. Looks like okay, but that's a zero, it's a number. So calculate the temperature in Kelvin of a temperature of 123 Celsius. So 0 Kelvin, okay, is equal to minus 273 degrees Celsius. So to convert from Celsius to Kelvin, it's very easy. Celsius to Kelvin, you just add on 273. You get kind of used to it. Seems weird first of all, but it's actually very simple. Okay. Is Kelvin not about degrees Kelvin, so we just got Kelvin like that. Okay, 1, 2, so 1, 2, 3. So just a little bit, tiny bit of maths. 1, 2, 3 plus 2, 7, 3. Okay, we're going to get we've got 6, 9, and a 3. 396 Kelvin. It's easy as that. Okay, so it says figure 2 shows results of an experiment to measure the changes in pressure of a gas for different temperatures when the volume stays constant. So we've got pressure, kilopascals, temperature. Okay, so as temperature goes up, pressure goes up. Kilopascals, thousands of pascals. Okay, so figure 2 shows the pressure of a gas is 50 kilopascals when the temperature is 80 Kelvin. Show using values from figure 2 the following equation is correct. So pressure divided by temperature is a constant value. Okay, so what you need to do is pick a different point. So we've got pressure, we've already got a point here, so we've got oh, here's my pen. Yeah, 50 kilopascals, temperature 80 Kelvin. What do we get from that? We keep the units the same, we don't have to convert anything. 0.625. Right, let's go. So he says using the graph. Okay, so it crosses kind of here. Okay, so it crosses directly. We want to choose an easy point, don't we? So we've got temperature. So this goes. So it's 100. So 20. So this is in 20. So let's look at the scale here. 20, 40, 60, 80. These go up in 20s. Okay, this is going up 10, 20. That's 50. Okay, yeah, it's going up. Obviously, we'll look at the scale because it's very easy to mistake scale. So here we've got temperature of 160 and pressure of 100. Okay. Ooh. Okay, 160 over 100. Okay. The calculator comes out. This is use a graph. You would have to use a graph. Only does that. .625. Okay. Yeah, that's correct. So yeah, so it proves it's a constant value. So they are the same. So it's a constant value, means it's the same. Okay, so I think that's all we've got time for this lesson. Okay, thank you for joining the class, and I'll see you in a different lesson. Thank you and goodbye.